Okay, so this is the picture of the red giant for a heavy mass star, because only in the heavy mass you get all these shells all the way going to inert iron core. In the low mass star, we learned that once you have formed carbon, nothing else happens, and then the carbon lump in the center of the star, that just drifts out into the space, interstellar space, and it's seen as a very hot core lump, which we call the white dwarf. But for the heavy mass star, you start forming all these heavier elements, and finally you form the iron. And the problem with the iron is that it cannot burn, it cannot get ignited. And if the iron core, is heavier than the Chandrasekhar limit, which is 1.4 solar masses, if the core is heavier than that, then it cannot even stabilize using the degeneracy pressure. Then something terrible happens. And what happens is that all the atoms, all the nuclei in the core, there's no longer any carbon, no longer any oxygen. All of that is crushed into a big lump of just the neutrons. So it's all mashed up into a giant nucleus. So it's like you have a atomic nucleus, but with like 10 to the 37, 38 neutrons in it. So it turns into a giant neutron lump, which is a kind of a matter which no one can imagine, no one has seen on Earth, but we believe that it exists in these stars. And this is a very cataclysmic event which produces huge amount of energy, and that is released, and it happens very, very quickly in a very, from the cosmic perspective, where things like take millions of years for stars is considered a short period of time. But this happens in within seconds. And as a result, you get a catastrophic event, which is called the super formation of a supernova. So the star collapses, the core collapses, turns into a neutron lump, which is very, very small. So it's so small that it's like the whole sun worth of mass is compressed into 10 kilometers, which is huge mass into very, very small piece of space. Now, uh, so So when this happens, this huge amount of energy which releases, and we also saw that also a lot of neutrinos are released. So this energy causes a big increase in it's like a big explosion in this space. So a star really bursts into a big explosion, and that we call the supernova. Supernovas are now routinely seen in galaxies, and we estimate that on average, one star per century in a galaxy goes into supernova, becomes a supernova. So you can expect to see one supernova per galaxy in 100 years. In our own galaxy, the last supernova, but this is just a chance. The last supernova was 1,000 years ago, which Chinese observed. But we were fortunate enough. We see these supernovas in faraway galaxies, but we were fortunate enough to see it in one of our neighboring galaxy. So one of our neighboring galaxy is called Large Magellanic Cloud because it was known for a long time and it was just a hazy spot in the sky. People called it cloud. There are actually two of them. There's Large Magellanic Cloud and the Small Magellanic Cloud, which you can see in this picture. Now we know that both of them are our satellite galaxies. They orbit around our own galaxy, the Milky Way. So in 1987, There was a supernova explosion in this galaxy. So with a telescope, you can resolve this galaxy and you can see these dust clouds and all these stars. So pictures are routinely taken of these things. So this is a picture before this supernova happened, and there was this star over here. And then it just exploded. This is a picture after a day. And you can see how bright it is compared to this. These are all these stars. You can imagine their light, how much they have cost on this photographic film, and compare it with this, what you see over here. So it's like billions of times more brighter than what you see over here. This is again the picture of this section of the Large Magellanic Cloud. You see all these dust, this galactic center, that's why it's bright. And imagine how much light you are seeing over here. So this is like the whole galaxy. It's the whole galaxy. That means this is the light coming from about 100 billion stars. And then over here at this spot, can you see my cursor? Over here somewhere, wait, let me activate the pen. Over here somewhere, something exploded. Well, not here. Sorry, it was here. So this is the picture after this supernova exploded. And you can see how bright it is. This is as bright as the center, maybe brighter than that. So when the supernova happens, you get an explosion which is as bright as 100 billion stars. And a huge number of neutrinos are produced, but when they're produced in a faraway galaxy, as you know that they do not interact very easily, and our detectors can detect a neutrino on the average of, like, if you have trillions and trillions of coming in, then only you have a chance of detecting only one of them. So we detect them from sun, but these supernovas, when they happen in faraway galaxies, we are unable to detect. But this, since this supernova was close enough, still about like still it's like 500,000 light years away, but still it was close enough that we detected the neutrinos. So what people saw, so these are some data points from these neutrino detectors, Comicon 2, these white spots, and the blacks are from another detector. You can see the time. Over a period of 12 seconds, they saw many neutrinos coming in, and they usually don't see it like that. Usually they see like about 10 neutrinos a day. And these neutrinos, they saw about 19 neutrinos within 10 seconds. So they were perplexed that what happened. And then they asked around, the astronomers told them that we saw a supernova at this time. And as expected, these were expected to come before the light from the supernova reaches, because supernova takes some time to heat up. So these neutrinos were observed just before the supernova explosion happened. And this is exactly what the theory predicted, that these neutrinos will be produced over a period of 12 seconds. The core will collapse within about 12 to 15 seconds. So all of this confirmed our theory of what happens in case of a supernova. So you were very fortunate to see this supernova explosion in a nearby galaxy in 1987. If something happens in our own galaxy, now we have even better neutrino detectors, and if something happens in our own galaxy, we will get even more neutrinos, and we will understand this process even better. This is again showing some data. This is some background. This is the intensity you see over time. And then suddenly there was a peak over here. So the supernova stayed there for some weeks. And then when people pointed their telescope in that region, what they saw is this kind of a remnant, this gas, hot gas, a wing of gas going out because of the huge shock wave which was produced. This is another picture. So it's going out. There are more wings around it. They're all going out. Very, very hot. They are radiating in X-rays. Radiating in X-ray means that they are at billions of degrees, close to billions of degrees. That's how hot this gas has become. This is in some other wavelength. You again see this. And there's this some outer gas, these wings. And over time, as you observe, they keep moving out. Similarly, there was a supernova in 1,000 years ago, which Chinese observed, and they marked its position. And when we point our telescopes in that direction, we see this explosion. It's like a remnant of something which exploded. This hot gas is still hot, not that hot as this one, because it has cooled down over 1,000 years, a little bit. So this gas is still there, it's going out, and by the speeds it's going out, if you run it back, you find out that it probably did happen 1,000 years ago. So it's the remnant of an exploding star. So when this star explodes, let me see, two things happen. Something which is extremely useful for us, well, I shouldn't say useful for us, is the reason that why we exist. Because where does all the things which, well, I shouldn't say we exist, probably we could have existed in some other way, because we are mostly carbon and nitrogen and those things, which are all produced inside these stars, inside the cores of stars. So initially we believe that the universe was made up of only hydrogen and helium, and that's what a typical cloud of gas in the interstellar medium is composed of, hydrogen and helium. And then when the hydrogen is cooked inside a star, then these heavier elements are formed. But as our story indicates that even in a heavy star, you can only form up to iron. You cannot form any nucleus which is heavier than iron. So where does all the other things come from? For example, where does the uranium come from? And all the other heavier elements? Well, we believe that when this big explosion happens, it's so hot and it's so cataclysmic that all kinds of the nuclei are pushed together into each other, and all kinds of heavy nuclei are produced, and this is where we believe that the heavier nuclei are produced. And then they're dispersed out, and all those materials which were produced inside the star and the new ones which are produced inside the star are dispersed out into space because of this supernova explosion. So this new, richer material then becomes part of nearby interstellar dust. And when the future stars are formed, future clouds from which stars are formed, this material is retained in them. And these heavier things then coalesce into planets. And that's where these heavier elements are, because the planets are formed of these heavier elements because they stick together. So our Earth, we can be sure, because it's rich in these heavier elements, carbon and whatnot, of which we are made. These atoms were cooked up in some star someday, which exploded, and then disperse this material, and it's a new generation of star which then forms these elements into its surrounding planets. So that's why they say that we are made up of star stuff. Now, what is left behind? So when this explodes, what happens to the center? So as I said, that the center is a lump of neutrons. And that is called the neutron star. Because it's just made up of neutrons. But there's another name for it. It's also called a pulsar because it pulsates. And it was first discovered, it was discovered independently. Astronomers didn't, those who discovered, they didn't know that this is what we should expect. There are these neutron stars. Well, people thought they should be there. But what happened was that, wait, just give me a second. There's a problem. So, wait, yeah. So Jocelyn Bernal, she was just a graduate student at that time, Jocelyn Bell actually, and she was studying some radio sources, because there are many different. If you look up into the sky, you find all kinds of strange things, and you look at different frequency range of light, you find different kind of phenomena. So what astronomers do, they study like normal light. Then some people say, okay, I'm gonna focus on infrared. Some people say I'm gonna focus on X-rays. Similarly, radio waves is a very, very important source to study. And the way you look at the radio waves, as you can see in this picture, to capture them, you need these kind of radio antennas. And it's like a telescope for you. So this telescope, to capture the radio part of the frequency coming from the skies, looks very different from regular telescopes. These kind of antennas, and you may have seen that now they make like an array of antennas. So they then act like a big antenna, very, very big antenna. So it's like a very big telescope to capture these radio waves. So she was studying these radio waves, and she found a very strange phenomena. So this is her actual notebook. she saw that these kind of pulsating. So there's this radio source and it's pulsating. There's a dip, there's a dip, there's a dip, there's a dip. And she was able to recognize that something is going on. And now we know, then these were analyzed more carefully. So it was, what's happening over here is you have this kind of a neutron lump which is left over. It has a huge amount of it spins at a very, very fast rate. Why it spins at a very, very fast rate is because it's just the same phenomena because of which if you see a figure skater, how do they spin very, very fast? They start with a certain spin, and when they bring their arms in, then they start spinning faster. So this is a phenomenon. If you spin something, the total amount of spin has to remain kind of constant. And that spin depends on how big an object is. If you contract the object, then to retain the amount of spin, which is called the angular momentum, the object has to start moving faster. Wait, let me probably show you. Video, let me see if I have the video. Let me turn the share. So can you see this YouTube video now?
Yes, sir.
Now look what she's gonna do. She's gonna start spinning at certain rate, but she wants to show a very fast spin. So what she can do is start spinning and then bring her body in. So reduce her size. So first start spinning with arms and legs stretched out, and when she brings those in, then the spin is gonna increase very rapidly. Let's watch it once more at a reduced rate. So now she's moving at a constant speed. She has no way to speed up because she's not now kicking the ground. All she's gonna do is bring her arms in, arms and legs. And that speeds her up. So that's exactly what happens in case of these neutron stars. Because remember what the core was big. It was made up of iron. And then the iron collapsed and it all went down to nuclear density. So it became extremely small. So because of it becoming extremely small, it starts spinning extremely fast. And it is spinning extremely fast, and it has because of that, it has a huge magnetic field. And what happens is, because of that magnetic field, all the light. So what is the light? Because it's extremely hot now. So most of the light is pushed towards far blue end of the spectrum, which is actually the X-ray spectrum. So you have these X-rays coming out of these, and they're all directed in a particular direction. So instead of light going in all directions because of the strong magnetic field, it's all directed in towards these cones. So this direction in a cone and this direction. And then on top, this is spinning like that. So this thing spins like that. So the source of light spins around. So this is the spinning axis, and this is the magnetic field, and this way is the source of light. So if we are standing here, we will see this light coming in, and then just disappearing and coming back, and then disappearing and coming back. So it's like a lighthouse. It acts exactly like a lighthouse, and we see pulses. Let me show you another video. This is the picture of this neutron star. And it's spinning. And this is the light source in particular directions. And if we are standing here, it will sweep us. We will see these sweeps. So that will appear to us pulses. And from far away, we see this kind of stuff. This kind of pulses. And since this thing is so small, and since it's moving so rapidly, so these pulses, they are very stable. So you see sometimes of these pulsars have like 1 pulse per second. So the whole thing is moving in 1 second, and sometimes even smaller. And they are so regular that you can time your clocks. Well, actually, even the very best made Swiss clocks cannot compete with their timing. And when the first time they were discovered, people were worried that how come, while like we are seeing these kind of pulses coming from deep space, which are so well timed, natural phenomena cannot give us such high precision timing. And these pulses, they were given the code names, not the code names, the catalog names, LGM. So the first one is LGM1. You find, for example, the 55th is LGM 55. And LGM stands for Little Green Men, because jokingly they said that probably is half jokingly, probably is coming from some intelligent beings sending the pulses, because otherwise, how can they be so precisely timed pulses? But now we understand it's because of this kind of a neutron star. So these neutron stars are not a fancy. We see them through these pulsars. They appear as a pulsars, and we see their rotation. These rotations change over time, and we can study a lot about them using them. And the other thing about neutron stars is that they are supposed to be extremely heavy, because they certainly are heavy. Some of them come in pairs, so we can measure their masses. There are things moving around them, gases moving around them, so we can measure their masses. And we can estimate their size, because if they're moving so fast, they cannot be big enough, because otherwise their surface would be moving at higher than the speed of light. So they are very, very small, and they're very heavy. So they're extremely dense objects. In fact, the density is about 10 to the about 100 billion kilograms in 1 cubic centimeter. So cubic centimeter is like smaller than a teaspoon, and that's 100 billion kilograms. Actually, yeah. So they're kind of very strange objects. So what you can test is there, so this, we saw this supernova, and if it is true, we saw the supernova, we saw the neutrinos coming from it, and if all of our story is true, there should be a pulsar source in the center of it. And there actually is. We can see this pulsar. It's in there. We see these pulses coming from there. And actually, you can go back to this one with the Chinese saw and try to find if there's a pulsar there. And sure, there is a pulsar at the center of this cloud as well. So it really was a supernova explosion. So this is all the story about the lives of stars. And now we have only one lecture left, and somehow we were not able to, because of various reasons, really cover what we wanted to do in this course. Well, we have essentially lost 4 lectures, but other than that as well, we have been, the pace has been slower than I expected. Now, I'm of double minds. We can discuss a little bit about galaxies, or we can stop here. And in the last lecture, we can just do some kind of a revision. What do you suggest?
We could stop here and do the last class as revision. I think that would be very helpful.
Yeah, so yeah, let's do that, because we have come to the end of, at least we have covered the story about stars. So let's not go into a new topic of galaxies. So let's stop here, and I'll send you a video, if I can find a link for it, where all the story is summarized by Carl Sagan. And let's do, in the next class, let's do the revision of the post-mid section.
Professor, I have one more question.
Yeah, and I'll also send you some homeworks like last time.
Okay, can I ask my question?
Yeah.
So everything that we've studied so far in the course, most of it is covered in the textbook,
Yep.
right?
Yep.
So we should use that as like supplementary reading for the final?
Definitely, definitely.
All right, all right.
So let me stop here. And yeah, okay.